Okay, this is Electude. This is Electude. I'm asking some electrical questions from my small check performance class level 1 for some of the students. Okay, let's walk through this. This first one, it says here, in a parallel circuit, the loads are connected separately. The advantage of the parallel circuits are, right, all loads operate in the same voltage equal to the source voltage. The loads can be controlled to operate at the same time or separately. That's the advantage of a parallel circuit. If one load goes out, the other one still works. That's how most cars hooked up in parallel or series parallel. So the first thing says connect the two large lamps in parallel. Here's the large lamps. We're going to connect those in parallel to each other. So you're going to go from here to there, here to here, here to here, here to there. Now I'm going to hit this and say check. Now watch what happens. Incorrect. Because this one is not connected all the way. Let's connect it. See current flowing through that one. This one is not flowing. Current leaving the battery, going through this light, back to the battery. That one circuit is flowing. Now, why is this one's not moving? Let's try this one again. Should get in the right spot. Now both lights have current flowing through it. This is a 2 ohm resistor. This is a 4 ohm resistor. Had current run through this one. You can see it's a large amount of current going through this one based off the resistance. And you can see this one. See how small this one is based off the resistance. But both lights are flowing. That's the advantage of a parallel circuit. One goes out, the other one still works. But look at this though. Look at the resistance. Less resistance, more current. The arrow represents the current. I say less resistance, more current. More resistance, less current. This is showing you how resistance affects current. Check it again, and that's right. Move this out the way. Connected 3 lamps in parallel. Let's do it again. That's circuit 1, current's flowing through it, 2 ohm resistor. Circuit 2, 4 ohm resistor. You can see the current's flowing through it. Now what you think is going to happen here? 6 ohm resistor. This is 2, 4, and then 6. What do you think is going to happen with the current on this one? Less current. See this? 2 ohms, more current. 4 ohms, less current. 6 ohms, the least amount of current. If you cut a wire between 2 and 5, what's 2 and 5? What's 2 and 5 at? Oh, right here. 2 and 5. Will lamps 2 and 3 still work? Of course it works, because we just seen it earlier. It's a parallel circuit. See? Parallel circuit. These two still works. Even when this light goes out, the other 2 legs still work. So I said yes. Remove the connector between 2 and 5. Oops. Click here, remove the connector. By clicking on it and then connect the ammeter between the 2 points. The current through R1 is. Now here's my ammeter. Now you could do this without the ammeter, but if I take 12 volts and use Ohm law and 6 ohms, 12 volts divided by 2 ohms. I'm sorry, I said 6. I should have 6 ohms. 6 current, 6 amps going through it. But anyway, let's see what they want. Let's go here. Amperage. Set on amps. Fit this here. Fit this here. You can see 6 amps. Ohm's law is correct. 6 amps. Now remove the connection from R3 and R6. R3 and R6. Do the same thing. Now remember, this is 4 ohms. Do the math again. 12 volts divided by 4 ohms equals 3 amps. Let's see if that's correct. See? 3 amps. That's correct. Now it says R4 and R7. What you think it should be? Now I'm going to leave it up to you. Where does the current run through this leg here? Let's find out. If you said 2 amps, you're correct. That's correct. Let's go to the next lesson in this module. What's the total current through the circuit? Now, we can add it up. If you remember what it was, we could add it up. If we add up each branch that we had last time, that we just did, add up each individual branch, we get the total current of this whole circuit. So find a total current in a circuit on Ohm's law. You add up the current in each branch or each leg. That gives you the total current. But you can see here we have an ammeter. Now this is a little tricky here. 10 millivolts equals 1 amp. 1 millivolt equals an amp. Okay? And it's a little tricky. And what you're going to do it, you can see here, we have it connect this to this. Before I do that, you notice that the black lead right here is hooked to the voltage, not the amperage, because we have to convert it over. So you hook this here, see a little plus sign there, put that around the line, and it's on. And it's, let's see here. No. What's going wrong here? It should be. Turn on. And meter on. Meter don't know. That blow a fuse or something. I think I did something wrong here. No current's flowing. My meter is not registering. What's going on there? Okay. That's AC. That's DC. I know I did. I had it on amperage. I had to put it on voltage. Forgot. See, I'm converting voltage. I had it on the amps. See, last time I had it down here. That's when it was in series. I had it wrong. Since I'm converting to voltage, I had to put it over here. Voltage. Now, my reading is 0.11. How many amps is that? It's one way you can do this. I could take this milliamps, 10 millivolts times an amp, and convert this to amps. It would be 0.010. Alright, so I take this 0.11 divided by 0.010. Now that's 0.01 volts. I just took the millivolts and made a volt. 0.01 volts equals 11 amps. Or just go with the decimal 1, 2, 11 amps. Write this as 11 amps. What would it do? 11 amps. So basically all I did was I converted this over to a voltage. That's millivolts. I made a whole volt, like a whole amp. I made a whole volt. 0.010. Milli is 1,000. So I moved the decimal 3 places to the left. 1, 2, 3. And times that by, and divided 0.11 by 0.010 gives me 11 amps. I lost my calculator. Oh no, where's my calculator at? Alright, so let's go to the next one. Now it says here, using the current amp, what is the total current through the circuit? Now we can add it up from the previous examples. And every branch will equal, current going through each branch is the total of the whole circuit. So what the current is going here, and through here, it's the total of the whole circuit. The complete circuit, I should say. But here we have an amp probe. You could take this amp probe and you can see 1 millivolt equals 1 amp. 10 millivolts equals 1 amp. So we could turn this on, put it on 1 millivolt. So every millivolt you see is going to equal 1 amp. So we're going to move this over to 200 millivolts. Put this on here. 11 amps. You see here, it's 11 millivolts. So we have milli right here, 11 millivolts. That means it's 11 amps. Now we could went to this one, go to a higher scale. That's a 110. Go to a 20 volt scale. Probably the same thing. So here we have 110 millivolts, 2 millivolts. On the 2 scope, you got 0.110, and the 20, you got 0.11. So in this case, we had to bring a calculator in, and I would make this 0.010 volts, 0.0. I would divide this 0.11 by 0.010 gives me 11 amps. Awesome. But you can see this is the direct reading here, more direct reading 11. Okay, the total current is 11 amps. What is the total resistance? Now, Ohm's law again. We have 12 volts and 11 amps. So we're going to say 12 volts divided by 11 amps equals 1.09 ohms, which is correct. Now, so what's the voltage drop across R1? Now, remember, this is a circuit in parallel. Okay? Here's the rule in the parallel circuit. The voltage drop should be equivalent to source voltage on the parallel circuit. In other words, if I go across this circuit and do a voltage drop across each leg, I should see source voltage. Oops. Oh no, I did. I blew a fuse. See? I never moved. That's an amateur mistake. I never moved it over. You can always move it over when you're done with the meter. This is why most fuses are blown in the shop. I didn't move it over. Let's try that again. 12. See? 12 volts, 12 volt drop. There's only one low in that leg, so it should drop to 12 volts. What? What? The voltage across R1 is not 12? Maybe not 12. Are you serious? They wanted to put the 0.0 down there. Electude. R2, the same thing. It's gonna be the same reading. No matter what the resistors are, because you know the resistance is different in each leg, it should still drop system voltage. In a parallel circuit, every leg drops system voltage no matter what the resistance is. Now let's go to module 2. Okay, it says here, the details of the diagram. Opposite are voltage 12 volts, R1 and R2, 4 ohms each, R1 and R2, 4 ohms each, R3 and R4, R3, R4, 6 ohms each, R5, 6 and 7, 24 ohms each, R25, R5, R6 and R7, 24 ohms each. Now it says, what is the current through Z11? Here's Z11. I'll open it up. I'll put my ohm meter, my amp meter over here. I'm going to put this on amperage. I stick this in series of the circuit. Oops. That's in series of the circuit. You can see 4 amps. Remember, the circuit has to be open. You put the meter in series. Alright, let's go to R2. It says, what's the total resistance? What's the total resistance of R3 and R4? This is R3 and R4. We already know it's 4 amps, right? You can do it like this. And we could get the calculator again. Calculator. And do this. 12 volts divided by 4 amps equals, my resistance is 3. God, I keep doing that. Calculate the current through Z. Oh, look at this one. Calculate the current through Z4. Now this one you can't open up. See? But they want you to calculate the current. So I can't use this meter. But we know it's R5 6 and 7 are 24 ohms. So we do it like this. How much current is going to run through this leg? How much current is going to run through this leg? How much current is going to run through this leg? Then we add them all up. Because basically just individual series circuits. That's the easiest way to do it. So we take 12 volt battery and divide it by 24. Come on. 24 equals 0.5. Now since they all the same ohms, 24, 24, and 24, they all going to be 0.5. 0.5 a current run through this leg, a half a current run through this leg, and a half a current run through this leg. Because they all the same resistance. Alright? So now it's actually you calculate the current through Z4. Here is Z4 here. So the current for these three legs have to run through Z4. Then they split up through each branch. Like half gonna go here, half the current gonna go here, and half the current gonna go through here. So you add it up, 1.5 times 3 is 1.5. What's the total resistance of R5, R6, and R7? Good question. Since we know the current is 1.5, so you're going to say voltage divided by current gives me resistance. 8. See? Next one. Calculate the total current flowing through the circuit. Now, hold on now. We want the current through the whole circuit. Everything now. And it'd be nice to have a clamp we can put over here. But we don't. That don't open. We could put an ammeter here to find out, but we don't have one. And it doesn't open up. So we have to figure out the current through the whole circuit. Alright. Now how we're going to do this is we're going to have to add up each individual one. Okay. So I have to write this down. So let's try this leg first. Remember, the current is the total current. The total current is equivalent to all the circuits added up. So we're going to do it one at a time. R1 and R2 is 4 ohms, right? So 12 volts divided by 4 ohms of R1 is 3 amps. R2, again, 4 ohms, 3 amps. So we got 3 amps here, 3 amps here. Next one, R3 and R4 are 6 ohms each. 6 and 6. So we got 12 divided by 6 is 2 ohms here, and 2 ohms here. So we had 3, 3, 2, and 2. Now in this one, we already know this 1.5. Okay, we just did that one. So let's add it up. 1.5, because we did this earlier. We know this 1.5 plus 2 and 2 is 4. And 3 and 3 is 6. So the total current leaving the battery to feed all these circuits, 1, 2, 3, 4, 5, 6, 7 circuits, should be 11.5 amps. Man, I'll do it again. And remember, all we did was treat each leg as an individual series circuit, even though it's parallel. We calculated the current goes this circuit, through this one, 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 as individual circuits by using the ohms they gave me up here. And the total current, when you add them all up, because remember, the total current in a parallel circuit, I'm sorry, let me say it again. The individual current going through each leg in a parallel circuit is the total of the equivalent voltage coming from the battery. And I should have 11.5. Oops. There we go. Next one. Calculate the total resistance of R1, 2, 3, 4, 5, 6, and 7. So we already know the resistance, the current is 11.5. So we get the voltage, which is 12 volts. So it's 12 volts divided by 11.5 equals, that's right. Try it again. 12 volts. Make sure I got that right. Divided by 11.5. 1.04. Let's see if that's right. 1.04. That's correct. So the total resistance of all these together is 1.04. And here's another rule. You know you're right. My total resistance should always be smaller than the smallest resistors, which is 4. Then you know you're on the right track. If it's more, you did it wrong. Oh, that's it.